Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communications. So in the previous module, we have started looking at a characterization of the wireless communication channel, and we have said that the delay spread is an important parameter of the wireless channel, and we looked at two metrics to characterize the delay spread. So what we have done in the previous modules is we have looked at two metrics for the delay spread parameter of a wireless communication channel. The first metric is the maximum delay spread, and the second one is the RMS delay. The maximum delay spread and the RMS delay spread, and we have looked at both these metrics as important. These are both these metrics to characterize the delay spread of the wireless channel. And now we would like to understand what is the impact of this delay spread. I mean, how does delay spread impact the performance of a wireless communication system, or what is the importance of this delay spread parameter in the process of wireless communication. So what we would like to understand is what is the significance of what is the, either we can say impact, what is the impact or also significance of this quantity delay spread on wireless communication. That is, what is the impact? What is the impact? How does delay spread impact the performance of the wireless communication system? What is its significance in the context of wireless communication system? For this purpose, let us consider a transmitted signal which is given as follows. Let us look at the following transmitted signal. So I want to draw a simple transmitted signal consisting of various symbols. For instance, this is, let us say, my transmitted symbol consisting of various symbols. I am going to label the symbols shortly, but let us say this is my transmitted. You can clearly see the various symbols. For instance, this is the symbol S0, this is the symbol S1, symbol S2, symbol S3, symbol S4, symbol S5, symbol S6, and so on. This is continuing with respect to time. So I have a basic transmitted. So this is my transmitted signal, or simply I can call this TX signal. This is my transmitted signal comprising of various symbols. So these S1, these different quantities, S0, S1, S2, and so on, these are the various symbols. These are the different symbols of the transmitted signal, and you can see these symbols S0, S1, S2, these are flipping between the positive and negative voltage level. So I have S0 is a positive level, S1 is a negative level, and so on. So this is a simple, this shows a simple example of a BPSK transmitted signal in a communication system, right. And also I have a symbol time. The concept of symbol time is very important in any digital communication system, because the digital communication symbol has digital symbols, and each symbol has a certain symbol time which is constant per symbol that determines the rate of the digital communication system. So T, this is the symbol time, this is an important, this is the symbol symbol time equals t. So, or t denotes the symbol time, that is the time per symbol, and therefore 1 by t is the symbol rate. 1 by t, which denotes the number of symbols per second, is the symbol rate of the digital communication symbol, right. So, in a digital communication system, each symbol has a certain fixed time, that is the symbol time. So, we have various symbols S0, S1, S2, S3, so on, which are being transmitted, and t is our symbol time. Now, let us look at a simple multipath wireless channel. Consider a wireless multipath channel with L equals 2. So, I have a 2 multipath component wireless channel, that is a wireless channel with 2 multipath components, and therefore, the channel can be modeled as we have seen, it is A naught delta t minus tau naught plus A1 delta t minus tau 1. So, since there are 2 multipath components, this is consists of basically 2 multipath components. Further, let us use another simplification. Let us take the simple case of A naught equals A1 equals 1. This is a simple scenario, and therefore, this channel model becomes delta of t minus t naught plus delta of t minus t1. So, I have a simple 2 component multipath channel with the amplitudes equal to 1. So, therefore, the multipath channel is delta t minus t naught plus delta t minus t1, where tau naught is the delay corresponding to the first multipath component, tau 1 is the delay corresponding to the second multipath component. So, what we will have is that when the signal is transmitted by the transmitter, it will be at the receiver, we will have one component which is delayed by tau naught, we will have another component which is delayed by tau 1, and these 2 components will then add at the receiver. So, this is our multipath wireless channel model. So, we have one component which is delayed by tau naught, let us say this is the direct component or line of sight component. We have another component which is delayed by tau 1, let us say this is a scatter component, and then we will get this direct component and scatter component at the receiver, and these 2 components will add at the receiver. So, this is our multipath. This is a simple multipath channel model for this wireless communication system. Now, we had the transmitted signal. Now, how will the received signal look corresponding to this multipath channel? So, the received signal will look as follows. So, let us now draw the received signal corresponding to the multipath channel that we have illustrated. Now, the received signal will look as follows. First, starting from t equal to 0, there will be a delay corresponding to tau naught, because the direct component we said is delayed by tau naught, and then we will have our signal symbol S of 0, followed by our symbol S of 1, followed by our symbol S of 1, S of 2, followed by S3, S4, S5, S6 and so on. So, we have first what we have is we have the signal that is delayed by tau naught, followed by symbols S0, S1, S2, S3, S4, S5, S6 and so on. Alright. So, this is the received signal corresponding to the direct component that is delayed by tau naught. Now, I will have another component which we have seen, because the multipath channel has 2 components. Therefore, I will have another copy of the signal which is delayed by which is delayed by tau 1. Therefore, I will have another component of the signal which is delayed by tau 1. Let us say this is equal to tau 1, and now my signal will have S of 0. The symbol S of 0 followed by S of 1, S of 2, followed by S of 3, S of 4, followed by S of 5, S of 6, and so on. Okay. So, we will have the signal that is delayed by tau 1, right. We have a signal that is delayed by tau 1 followed by the same signal S of 0, S of 1, S of 2, S of 3, S of 4, S of 5, S of 6, and so on. And now what? So, this is, so if I have to mark this, so I have two copies of the same signal. One is delayed by tau naught, that is the delay of the first path. The other is delayed by tau 1, the delay of the second path. So, I have drawn these two signals here. So, this is signal copy or signal delayed by tau naught, and this here is signal delayed by tau 1. And now these two will add at the receivers. Now these two signal copies signal copies will add at the receiver. Now you can see something interesting that is happening when they are adding. Now because this tau naught, now let us look at this relative delay here. This is a key here. Now let us look at this relative delay. This relative delay is equal to tau 1 minus this here is equal to tau 1 minus tau naught. Now this tau 1 minus tau naught is greater than the symbol time, which is t. And therefore, what you will see is when these two signals add here at the receiver, S1 from the signal delayed by tau naught will overlap with S naught, S1 will add with S naught. Similarly, S2 will add with S1. Similarly, what you can see here is S3 will add with S2 and so on. So, what is happening is, in the signal delayed by tau naught, since tau naught is smaller than tau 1, S1 in the signal delayed by tau naught is adding up with S naught in the signal delayed by tau 1. Similarly, S1 in the S2 in the signal delayed by tau naught is adding up with S1 in the signal delayed by tau, and so on. So, what is happening here is these different symbols are adding up with each other, or these different symbols are interfering with each other. So, what is happening? Because these two different signal copies are delayed by these two different amounts, tau naught and tau 1, right. When these two different signal copies add up at the receiver, different symbols are aligning, and these different symbols are adding up, or these different symbols are interfering with each other. This phenomenon is known as intersymbol interference. So, this phenomenon where these different symbols are adding up, this phenomenon is termed as, this is precisely termed as or it is also denoted by ISI. So, this phenomenon is denoted by ISI. So, when this relative delay, now look at this, when is this happening? When this tau 1 minus tau naught, that is the relative delay between these two signals, is the signal copies is greater than the symbol time, that is t. So, when t2 minus, when when tau 1 minus tau naught is greater than t, then different symbols interfere with each other, and this is termed as, this is basically termed as your inter symbol this is basically termed as your inter-symbol interference or ISI. But now look at what is tau 1 minus tau naught. Tau 1 is the delay of the last arriving signal component, tau naught is the delay of the first arriving signal component. So, tau 1 minus tau naught in this scenario is nothing but the delay spread of the wireless communication channel. So, what is this quantity tau 1 minus tau naught? This is the delay spread sigma tau of the wireless communication channel, and when this is greater than t, that is the symbol time, we say that it leads to inter-symbol interference. So, the main principle, the main impact of the delay spread in a digital communication based wireless communication system is the following thing. If the delay spread is large, that is if the delay spread sigma tau is greater than the symbol time, then this leads to inter-symbol interference. If sigma tau is greater than t, that is the symbol time, what is happening? This is leading to ISI or inter-symbol interference, and ISI is bad because it results in distortion of the received signal. So, now we say ISI is undesirable since it leads to distortion of the original transmitted signal. So, what we are saying is this ISI, if these different symbols interfere at the receiver, it leads to a distortion of the original signal that has been transmitted. Therefore, ISI in the wireless communication system is undesirable, which means we need the delay spread to be smaller than the symbol time, because if the delay spread is larger than the symbol time, it is leading to inter-symbol interference. Therefore, ideally we need the symbol time to be smaller or the symbol time to be larger than the delay spread to avoid ISI. So, to avoid ISI, we need symbol time to be, larger than the delay spread. That is, we can write this criterion as follows: if symbol time is larger than the delay spread, if symbol time is larger than the delay spread, this implies no ISI. On the other hand, if symbol time is smaller than the delay spread, then there is going to be ISI. If the symbol time is smaller than the delay spread or the delay spread is larger than the symbol time, then there is going to be ISI. Now, what we want to see is what is the typical delay spread of a wireless channel. What is the typical delay spread in our common wireless channels that we encounter every day in a wireless cellular network. So, what is the typical delay spread what is the typical delay spread of a wireless channel. Now, to understand this, consider a cellular scenario. Now, in a typical cell, what is the distance of what are the distances in a typical cell? In a typical cell, the cell radius is around a couple of kilometers, right. So, let us look at a typical hexagonal with, let us say, we approximate it by a base station at the center of the cell, and there is a mobile towards the edge of the cell. So, this is the base station, this is the mobile, and the cell radius is of the order of kilometers. Now, what we have is we have a direct path between the base station and the mobile, and we have, let us say, a scatter path between. So, this is my non line of sight. So, this is my line of sight and this is my non line of sight path. Now, the cell radius is of the order of kilometers. So, we are saying that the cell radius is of the order of kilometers. Now, therefore, now if I look at these line of sight and non line of sight paths, that is, if for a cell phone at the edge of the cell, that is cell phone which is towards the boundary of the cell, if we look at this line of sight and non line of sight, if we look at these paths are generally of the order of kilometers, right, because the distances are of the order of kilometers. Therefore, my LOS and non line of sight paths are of the order of kilometers. Let us say, take a simple example. For instance, the line of sight path might be 2 kilometers, non line of sight path might be 3 kilometers, because non line of sight distance is typically greater than the line of sight distance. Line of sight distance is the shortest distance, right. Now, therefore, the distances are of the order of kilometers. Now, the important point you have to observe here is that the differences in the distances, that is, the difference in the distance, if I call that as delta D. Now, delta D equals the difference in distance. Now, since the distances are of the order of kilometers, delta D, which is the difference of the distances, is also of the order of kilometers. Therefore, what we have therefore, the difference delta D is also of the order of kilometers. Now, remember, I am not saying that delta D is exactly equal to 1 kilometer or exactly equal to 2 kilometers, because one cannot exactly say that this difference in distance is so much, because it depends on scenario to scenario. What we are saying is roughly the difference in distances delta D is of the order of kilometers. Now, therefore, the delay spread, which is basically arises because of the propagation delay between the line of sight and non line of sight and the various other components, that depends upon the difference of the distances, and therefore, the delay spread is given as the difference in the distances divided by the velocity. Therefore, the delay spread equals the difference in the time of arrival corresponding to the line of sight and non line of sight components. That corresponds to basically the difference in the distance, because why is there a delay between the line of sight and non line of sight components? Because the distance involved in the line of sight and non line of sight components is different, and therefore, the difference, the delay spread is equal to the difference in the distance divided by the velocity, that is delta D divided by C, and we have already seen delta D is of the order of a kilometer, let us say 1 kilometer, divided by the velocity of light or an electromagnetic wave, which is 3 into 10 to the power of 8 meters per second, and this is equal to basically 3.33 microsecond. So, the outdoor delay spreads in a wireless cellular channel, in the outdoor wireless channel, we are saying are approximately of the order of microseconds. That is, we have derived of the order of 3.33 microseconds. They are generally between 1 and 3 microseconds. So, delay spread is the order of approximately 1 to 3, between 1 to 3 microsecond. Typically, an average value we can take for practical context to use in our calculations. The typical value of a delay spread is 2 microseconds. So, typical outdoor delay spread. So, this is an important number to keep in mind for analysis. Typical outdoor delay spread of our wireless channel is equal to 2 microseconds. So, typical outdoor delay spread is equal to 2 microseconds. And now we had seen that if the delay spread is greater than the symbol time, then there is going to be inter-symbol interference, which means if t is less than 2 microseconds, if t is less than sigma tau is equal to 2 microsecond, implies there is going to be inter-symbol interference. If t on the other hand is greater than sigma t equals 2 microsecond, then that implies there is going to be no inter-symbol interference, and this is an important aspect. So, what have we done? We have basically now derived, analyzed what is the impact of the delay spread on the signal at the receiver in a wireless communication system. We have said that if the delay spread is large, that results in inter-symbol interference. How large? If the delay spread is larger than the symbol time, then that results in inter-symbol interference. And we have said that typically the delay spreads in a wireless, outdoor wireless channel are approximately 2 microseconds, which means if 2 microseconds the delay spread is larger than the symbol time, or symbol time is smaller than 2 microseconds, then there is going to be inter-symbol interference. On the other hand, if the symbol time is larger than 2 microseconds, then there is not going to be any inter-symbol interference. This basically summarizes what is the impact, what is the typical value of the delay spread in a wireless cellular network, and what is the impact of this delay spread on wireless communication. How does it lead to distortion in the signal at the receiver in a wireless communication system. Alright, so this clarifies important ideas about inter-symbol interference of the transmitted signal and the impact of and the role delay spread has to play in this context. So we will end this module here. Thank you very much.